So I changed my office hour to 2 to 3 p.m. tomorrow because there is another TA doing 4 to 5. I don't want to have overlap, so you can have more chance for office hour. So that's one thing. Another thing is that make sure you put in your participation point. So far we have one donut for the whole class. That's not enough. I know there's a lot of more of you that ask questions during class. Make sure to put those points in. All right. Any other question before we start? Yeah.
I know it's happening for other people, but when I log into iClicker, it says access denied. It's happening for a couple of us, so it's like a lot to say like 50 billion selfies. So I'm just letting you know.
Are you in this class right now? Like for this class, iClicker?
Yes.
Well, yeah. I mean, if it keep happening, just uh, yeah. I'm not the one running iClicker, but just always.
So I just said you.
Yeah, just keep taking selfie. Yeah. Yeah.
It's not good for me. I just do like one selfie with the whole class. So
Yeah, no, I have to take that.
Every question. Yeah. You can take group selfie if that saves you some time, but yeah. Any other question? Alright, let's start. Is it recording? Yes, it's recording. So today we're going to talk about lenses. This is a concave mirror. What a concave mirror do is not here. I have to go back to first page. What a concave mirror do is when there's light parallel to the optical axis of the mirror, like comes in, it will get reflected and pass through this point. And for other light that is also parallel to the optical axis, it will be reflected and pass through the exact same point. That's the design of a concave mirror. We have a real one here. Here's a real concave mirror. You can take a look of how you look like in the mirror. So, because this point is so special that all the parallel light will pass through this point, we call this the focal point because it focuses the light at this point. And the distance between this point and the mirror is called the absolute value of focal length, because in this class, the convention your textbook is using will sometimes make it negative. Sometimes focal length will be positive, sometimes the focal length will be negative because they want to write the formula in a certain way. Therefore, that's why I added absolute value here, so you know this is the physical distance. So this distance is what we call the focal length, the magnitude of focal length. Okay? So just some terminology. Here we have another example. I can show you that if I have a concave mirror, that indeed all the parallel light should be focused into one point over here. So that is a concave mirror. So far so good? Alright. So if instead of parallel, you go the opposite, you shine a light that passes through the focal point, the way it will get reflected is by, like, the reflected light will become parallel to the optical axis. Same with all the other light. As long as you pass through the focal point, then it will be reflected in a way such that it becomes parallel to the optical axis. Any question? Okay, now it's your time. Show me you know what is a concave mirror. So the light is this one. Here's a light that passed through the focal point and got reflected by the concave mirror. Which one should be the reflected light if you're actually looking at a concave mirror? If you're already done, you can have a peek of how the thing looks like, how yourself look like in the mirror. It's a concave mirror. What you're looking at is the image formed by the concave mirror. You will see that sometimes it will be upside down, but sometimes it will not. Good. So when a light passes through the focal point, it must be reflected in a way such that it becomes parallel with the optical axis. Okay? All right, next. So now we can look at how the concave mirror will form an image. You saw yourself in a mirror earlier. Now we're going to analyze exactly how that happens. What we're going to draw is the light ray diagram. If the top of this arrow emits some light, one of them will be parallel to the optical axis. And we know the one that is parallel to the optical axis will pass through the focal point after it gets reflected. Now, just one line can only tell us that the image of this arrow will be some point on this line, but we don't know exactly which point yet. Therefore, we must draw another light ray to help us figure out the location of the image. The other one we choose will be the one that passes through the focal point, because we know if this light ray passes through the focal point, it will be reflected parallel to the optical axis. And then we see that if you are looking at the light from this part, you will think that the light coming from the top of the arrow is coming from this point, which means you will think that the arrow is located at here. So the image formed by this concave mirror will be at here and upside down. And I use dotted line for the image. So that is why right now you should see yourself being upside down in the mirror. Okay? Any questions? So yeah, any questions? This will be the main theme of your homework this week, just drawing this light ray, finding the image. Now, some of you may have seen that your image inside this concave mirror will not always be upside down. If I bring it close enough, you should see an upright image, not upside down anymore. So you know that the way it creates an image depends on the location of the object. Let's look at how the image will be formed if the object is very close to the mirror. Again, parallel light will pass through the focal point. And to figure out the second light ray, we pretend a light ray is coming from the focal point. And then we follow this direction to draw a second ray. Because the direction of the second ray is the same as if it actually passed through the focal point, it will be reflected such that it will be parallel to the optical axis. Okay? So this trick is to draw some dotted line, and if the dotted line passes through the focal point, then the line following the direction will be the same as if it actually passed through the focal point. Now, if your eyeball is over here, and you see this light ray and this light ray, your eyeball will trace back and think that the light comes from this point behind the mirror, and it will be upright. So when you are really close to the concave mirror, you should see an upright image. You should see an upright image. If you don't have a chance to see it, you can come over later when the class is over. So this is why the image will be upright if you are close enough to the concave mirror. Any question? All right. Now again, let's review your memory about the lateral magnification. Now we see there's two ways to form an image. One is like this, one is like this. The definition of the lateral magnification is the ratio between the size of the image and the object, the lateral size, the vertical one, not the horizontal one, the vertical one. We know if it is inverse, it will be negative, but now I only care about the absolute value. So if I look at how many percent does the image or how many percent does the object get magnified in the lateral direction, which one should be a bigger value? So the definition is the height of the image divided by the height of the object. In this case, you see the image is taller, so you know the lateral magnification is bigger than 1. Here, the image is upside down, it's negative, but let's only look at the absolute value. The image is shorter than the object, so you know the absolute value is smaller than 1. So this is kind of like 0.8, and this is 1.2. So B will be bigger. Okay? Any questions? Now, be careful. This doesn't mean that the upside down one will always be smaller. We can look at another scenario, which the object is at here. Again, parallel light pass through the focal point, becomes parallel. And you see in this case, even though the image is also upside down, the lateral magnification is negative like 1.2. The image is still longer than the object. So you see, for the case of forming upside down image, the image might be shorter or longer depending on the position of the object. And now you should ask, at what location will the image be exactly the same in the vertical length as the object? And you can convince yourself by drawing that it happens when the object is twice the focal length away from the mirror. You see, when this is twice the focal length, these two triangles will give you some relation that I won't question you right now, but you should know by the time the final comes. Anyway, if you have a nice ruler and you draw carefully, you should see that if you put it twice, if you put the object at twice the focal length away from the mirror, then the image will be exactly the same in the size. Okay? Alright, more terminology. We saw that here, the two light rays actually pass through the point where the image is located. But here, the image is located at some point which the light doesn't really actually pass through. Your eyeball will think that the light comes from that point because the direction of the light seems like it comes from that point. But the physical light ray itself never actually passed through this point. So in this case, we call this a virtual image, while the case over here is called a real image. When the two light rays actually pass through that point where the image is located, it will be called a real image. And when you have a real image, it will be actually possible for you to put a screen at the location of the image and then project the image on the screen. So here, this is not a concave mirror, but I can show you what a real image looks like. Alright, it's dead. Never mind. Oh, it's actually dead. Alright, never mind. So the thing is that if you put a screen over here, then you will see the image on the screen. Here, if you put a screen behind a mirror, you won't see an image on the screen because the light ray didn't actually pass through there. So that's the difference between virtual and real image. Okay? Alright. So, next we can look at concave mirror, a convex mirror. A convex mirror is curved in the opposite direction. The way it deflects the light is by having also a focal point. But this time, the light ray doesn't really get focused at the focal point, but it will be reflected in a direction that kind of resembles the focal point. So the way the light ray will be reflected is such that if you extend the light ray, there will be a dotted line that passes through the focal point. So that is what a convex mirror will do to the light. We do have a convex mirror over here. What happened here? Okay, so here's another convex mirror. So you'll see overall what it does is that it will make the light diverge. If I have other light ray that is also parallel, it will be reflected such that the extended line will pass through the focal point behind the mirror, like this. So this is what the convex mirror will. This is what a convex mirror will do, and we also call this lens the focal length. So you might guess that the sign will be different between concave and convex mirror. That's true. What they will tell you is that the focal length of convex mirror is negative, blah blah blah. But don't worry about that right now. This lens is what we call the focal length. Okay. Now, if I have a light ray that come into the mirror about to pass through the focal point, then it will be reflected parallel to the optical axis. This is just the same thing going reverse. So if you have a light ray that will pass through the focal point if the mirror is not there, it will be reflected such that it is parallel after it gets reflected. So that is what a convex mirror will do. And oh, good. So if you look at your image in the mirror right now, you should become smaller and upright. And we can explain it again with drawing the light ray diagrams. If you have an object, light ray come in. If it is parallel, then it will be reflected such that the extension passes through the focal point behind the mirror. The next one is tricky. We want to draw it in a direction such that if you keep drawing it, it will pass through the focal point. The reason we choose this light ray is because we know we know how it will be reflected. It will be reflected such that it becomes parallel. There are other light rays that the object emits. They will all be reflected to the same point. No, never mind. So the reason we choose these two light rays is because we know how it will be reflected. And once you have two light rays, you can find the location of the image. Now, when you have these two light rays, your eyeball will think that the light from this point comes from this direction and this direction. So your eyeball will extend the light ray along the direction that is coming, and it will think that the image is here. Okay? So you see the image is shorter than the object. That's why it looks smaller in this convex mirror, and you see it is upright. Okay? So that is how the convex mirror forms an image. Any questions? The whole point of this class is to teach you how to draw light ray diagram. Make sure you know how to draw it. Ask questions whenever you have one. Alright, now, question time. Is this a real image or a virtual image? So this is, okay, this is fine. A real image is an image like this, which the light actually passes through the point that the image is formed. So I can put a screen over here, and you will see the image on the screen. I don't think it is good enough. So in this example, this is a real image. So I can put a screen over here, and you can see the image is actually over here because the light actually passes through this point. Now, does the light actually pass through that point? Is the image formed by this convex mirror a real image or not? Good, it's a virtual image. You see, the light never actually passed through this point. This dotted line is the extension along the direction that the light comes from. There's no light that actually goes behind the mirror. The mirror reflects the light. There's nothing here. If I put a screen behind the mirror, I will not see any of your image. That's why we call it a virtual image. Okay? Any question about real virtual image, the definition? Yeah? Not true. You will see a lot of different scenarios. Any other question? Do not judge the location or real not. Don't judge if the image is real or virtual based on the location or orientation or whatever. There's no universal rule. The only universal rule is to draw a light ray diagram for every scenario, and then you'll figure out the orientation of the image, real or not, and should it be bigger or smaller. The plan is to make sure you know how to draw it in 10 seconds after this homework. Okay? Any other question? Okay. Now, so before we move on, let's remember which one is which. Let's remember the name. So if you have a concave something, then it looks skinny. If you have a convex something, it will look kind of chubby. So we interpret it as a pregnant creature. This one is not pregnant. So if you behave, you stay concave. If you have sex, you became convex. All right? So do you guys remember which one is which now? This works the same for other type of optical device. When you see something that have a cave, it goes inward, it's skinny, it's called concave something. Concave mirror, concave lens, and if it is not a cave, then we call it a convex mirror, concave lens, concave lens. Okay? Any question? All right. So here we see you can form interesting image with reflection. Reflection can change the direction of the light. That causes the image effect. There's another way we can change the direction of light, which is by refraction. So let's say we have a material with refractive index bigger than this. So it means the light goes slower. It can be water, it can be glass, and you have a point light source inside of the glass. When the light comes from this point light source and it hit the interface between the glass and the air, it will be refracted. The law of refraction is that you draw this normal line, normal to the interface that the light ray passes through, and in this case, because it is a spherical refractor, this is a part of the circle centered at this point. So if you draw the radius and extend the radius, this dotted line will be normal or perpendicular to the interface that the light passes through. Now, when you go from slow to fast, it will go away from the dotted line. So the light ray will be bended downward. So that is one light ray coming from this red point, and your eyes will think the light ray comes from something over there, somewhere over there. But now, you can draw another light ray also coming from this point. Just go straight. When you just pass through the interface vertically or perpendicularly, it cannot bend up or down because it's symmetric. Up, down looks the same, so it must keep going straight. Here, the light ray is bent. The light ray is to the top of the dotted line, so it will become to the bottom of the dotted line, and it will bend away from the dotted line if you go from slow to fast. That's why it goes like this. Here, it just goes straight, and you see they intersect at this point. So if your eyeball is further away from here, you will think that there's a point source at this point because the light all comes from this point. Therefore, you will think that the point source is not in the glass, but somewhere in front of the glass. This is how this spherical refractor forms an image by refraction. Any question? Yeah. Should it be refracted up or down? So if you draw the dotted line, for the bottom ray, the dotted line have to be perpendicular to the surface. So now the upper edge of the whiteboard is the dotted line. You see the dotted line is parallel to the red line. So it's symmetric up and down. Okay? The dotted line need to be always perpendicular to the surface, like this, and when you go to this line, the dotted line becomes horizontal. So it is symmetric up and down. You don't know which direction colors bend away from the dotted line, so it just doesn't bend. Okay? Good. Any other question? All right. So just like the image formed by a concave mirror can have different scenarios, we can look at a scenario which the light source is closer to the interface. Again, a light ray that enters the interface from slow to fast should bend away from the dotted line. So it will go a little bit downward. But because this time the light source is closer to the center of the sphere, the light ray after bending still goes upward. Now, this horizontal line still passes through this point, which the dotted line should also be horizontal, so it couldn't bend up, it couldn't bend down because up down looks the same for it. It doesn't know where to go, so it just keeps going straight. So in this case, where's the image? There's a cool function which I believe you can draw like the square. Yeah, so I think you can kind of circle a region on the slide. So try to circle where should the image be formed on this scenario. Just draw a square, see where you think the image should be formed. Right now the light ray is not intersecting, so does it mean we don't have image? The point source just disappear. So we have some population over here, some population over here. This is not a trick question. This doesn't count. So it is good that you know the real image will be on the light ray. So in this case, the image is on the light ray. But the reason that the image is on the light ray is because the light ray intersect at this point. So it will look like the light is coming from this point. Here, the light ray doesn't intersect into a point. So your eyeball will just keep follow the direction that the light comes from or appears to come from. Your eyeball doesn't know there's a glass and the refractor and stuff. Your eyeball only knows that the light ray comes from this direction, and if you follow that direction, you'll see that there is a point which both lines seems to came from altogether. So your eyeball will think that the light comes from this point because if you follow the direction, that's where the point source appear to be looked at. And this will be a virtual image. Okay? Yeah.
So the first one was a real image, the second one was virtual.
Good. This is a virtual image. And this is a real image. Any other question? Do you guys get the feeling of how this game is working? How this game works? Just draw lines, and if they don't intersect, try to draw dotted line in the opposite direction. All right. Now, so you see here, the image is on the left, but here, the image is on the right. Somehow, there's a connection from right to left, because this is the same exact refractor. You can just move the object around, and somehow you should have a transition from right to left. This is because when you move it at a specific distance, you will see that these two lines just becomes parallel, and they will not form an image, or you can say the image is at infinity. When you move the light a little bit to the left, the image is at here. So when you move the object farther away from the interface, the image is at here. As you move closer and closer, the image will move farther and farther to infinity, and apparently plus infinity and minus infinity is connected. So as you move even closer, the image will be formed at the left-hand side of the refractor. It goes all the way to the right and then come back from infinity. Okay? So this specific distance is the one that separates the two scenarios. If the object is further than this distance, it will form a real image on the right. If the object is closer, it will form a virtual image on the left. Okay? And the distance, this spatial distance, depends, of course, on the refractive index and also the curvature of the sphere. Any question? All right. So, of course, we can have a scenario which the object is not inside the refractor, but outside the refractor. Here, this is glass. The refractive index is bigger, and we draw the same. We do the same trick. When the light ray enters an interface of two medium, it will be refracted. But this time, it's from small refractive index to large refractive index, which is fast to slow. When you go from fast to slow, it should be refracted toward the dotted line. Okay, so it got bended downward a little bit. When you go from when you go from slow to fast, it got bended away from the dotted line. When you go from fast to slow, it gets bended toward the dotted line. Now, the second line is also easy. You just draw a straight line, and because it enters the interface perpendicularly, it doesn't get bended in either direction. It's symmetric. And here you see another scenario which the light ray doesn't really intersect. And what you do is to just go backward and see if there's any point that the extended light intersect each other, and indeed there is. So in this case, it will also form a virtual image. Okay? Any other? Yeah?
What if for the second line I don't want to draw a horizontal line? Like, I want to give it an angle or something.
Well, then make sure you have a clear geometric software built in your brain, so you know how exactly, you know what angle should this be bended, and then you can find the location of the image. There are different rays that you can draw, and if you draw it correctly, will give you the right location of the image. I'm just showing you the easiest way, but feel free to explore other way. Yeah.
Can you clarify what you mean by the revert being slower?
Good. So the light ray will actually travel slower in the glass. That's the cause of refraction. So let's go back to the previous lecture. This is lecture 3. So when the light ray goes into the glass, the light is a wave becomes slower, but the frequency is the same, so you know the wavelength should be shorter. And when you go in the angle, you see the wavelength should be shorter, so it must bend toward a other direction. So that's what I mean by when you go from fast to slow, the wavelength goes from long to short, and geometrically you can see it means the direction of the light ray must be bended because light is a wave. Okay? Any other question? All right, let's go back to the lecture today. So remember, this is made with glass. There's shape, there's the material, which the refractive index tells you which one has faster wave speed. The bigger the refractive index, the slower the wave speed, because it is a measure of how slower, or this is a measure of how much it can slow down the wave. The bigger the index, the slower the wave got slowed down. All right. Now it's free question time. You see the refractor. And what property of the refractor do you think will affect the location of the image? We know the location of the object will change the location of the image. That's just trivial. When you are an engineer, you don't have access to what object the client wants to put in front of the mirror or the refractor. So what property of the refractor itself will affect the location of the object? Angle? You need two straight lines to form an angle. The refractor doesn't. The refractor is the blue thing. It's the glass part. It's a sphere. It doesn't have an angle. Index, good. The refractive index. Or curvature, good. So there's two things you can control over here. The refractive index, which controls the speed of light in the glass, and the curvature, which is the shape of the refractor. You guys have done the imaging for a plane refractor in your homework. You can see it kind of work differently. So light curvature does affect the location of image. And the thing I want to focus on right here is the material, which is the refractive index. So let's say I have refractive index 1 for air or vacuum, and the glass I'm using now have refractive index 1.5. I can change the glass into different type of glass, but with the same shape. I hope your eyeball can adjust to the color. Here is still the glass. I make the color fainter because I want to represent the refractive index become smaller, which means it doesn't slow down the wave that much. Here, you see a significant slowdown of the wave and the light rate get bended a lot. If the refractive index becomes closer to 1, it doesn't get bended as much. And if you keep decreasing the refractive index, the light rate should not be bended as much. It becomes straighter and straighter, or just get closer to the original direction. And you know the effect should be that the image will become closer and closer to the original location of the object itself. So what we learned is that there is a tendency that this thing should follow. Even though you haven't learned all the math, the geometry, but you should know just by drawing or just by how refraction works, that if the refractor have the same refractive index as the air, then there's no change of speed of wave. If the speed of light doesn't change when it enters the refractor, then it shouldn't get refracted. And in this case, it should act as like there's no refractor at all, and the object and image should end up with the same location. Okay? That is a hint of your homework. Any question with the refractor? Okay, now we enter something you are more familiar with, like you wear in front of your eyeball, some lenses or your glasses. This is a convex lens because you see it looks like it is not concave. And the way a convex lens works is that when you have parallel light coming into the lens, it gets focused onto a focal length like this. All the light that pass through the lens, as long as they are parallel to the optical axis, it will pass through a single point, which we of course call the focal point. Here I have a real one. So this is a convex lens. You see it does get focused to a single point. Similarly, you can go backward. Instead of parallel to one point, you can go from one point to parallel. Now, usually, those two lines are what we draw for mirrors. You draw one parallel, and you know it will be focused to that point, and you try to draw another line going through that point, and it becomes parallel. For lenses, there's another line that's more easier to draw, which is the line that passes through the center. So if the lens is thin enough, which we always assume, then you will see the light that passes through the center doesn't really get bended to another direction. This is an approximation which we always make. We are looking at thin lens. So you can say, shouldn't there be some shifting vertically from here to here? Well, those are negligible. What we do is that if the lens is thin enough, then as long as your light ray passes through the center of the lens, it just keeps going straight. And you know it's very easy to draw because you don't even need to change the direction. You just put your ruler and then draw a straight line. Okay? So how do we use this property to figure out the location of the image formed by a convex lens? First line, parallel, because we know if it is parallel, it will pass through the focal point. So that's one line down. The second line we can choose is the line that passes through the center of the lens, because we know if it passes through the center, it doesn't get deflected. It just keeps going straight. So now you see the light ray pass through a point. So when your eyeball is over here, you will think that the light coming from this point actually comes from this point, because that's where the light appears to come from, and you will have an upside down image. That is the case for this one. What we have here is a convex lens. If you try to look at the projector or look at me through the lens, I mean, I can see you guys upside down right now, so you guys probably will not see me upside down. It's not how it works, but this is a convex lens. And now we have Elmo, a character from Sesame Street. Based on this drawing, I should get an upside down Elmo. And I think you guys have seen it already, but let's see again. you will see indeed Elmo becomes upside down. Okay? Upside down Elmo. You will have chance to play with this thing in your lab sometimes in this month or next month before the quarter ends. Alright, so this is how a convex lens works. Any question? So if you are far-sighted, you will be wearing a convex lens. But if you are nearsighted, what you are wearing is not a convex lens, it's more likely to be a concave lens. So a concave lens is something that when a light comes in parallelly, it gets deflected away following a dotted line, such that if you extend the dotted line, it will pass through some focal point. We have some convex lens over here, like this guy. So the overall effect is that the light gets spread out. This one has a not so obvious effect, but if you look at the drawing on the slide, you see if all the line got deflected away such that the extension behind the light ray will pass through a focal point, then the effect of this concave lens is to make parallel light go diverse. It will diverge the light. Okay? And if you want to go backward, then you have to aim the light at some point you will have to aim the light at some direction that is about to pass through the focal point, and then make it parallel. So that's kind of hard. Another better choice is to just draw a line that passes through the center of the lens. Just like convex lens, for a concave lens, if you pass through the center, you just keep going straight, no matter which direction you pass through the center. Okay? Now, let's look at how the image will be formed by a concave lens. So, first line, as always, our best friend, parallel line. In this case, for concave lens, a parallel line will be diverged in a direction following this dotted line. So, it goes that way. The second line can be chosen to pass through the center of the lens. So now we see that these two light rays doesn't really intersect each other, but our eyeball will just follow the dotted line backward until it thinks that the light is coming from a point. So in this case, you see a concave lens will form a virtual image at this location and smaller. If you have glasses, you can try it right now. I do want to emphasize that the light ray coming from this point is not just these two. There's light ray spreading spherically in all directions. It's just that these two directions is easier for us to draw by hand and predict the result. So there will be light ray between these two light rays, and the way it got deflected is somewhere in between, such that it looks like all the light ray comes from this point, as long as you have a good enough lens. If you just pick a random glass, then of course it's not going to have a perfect image. Alright, any question with how lens work? Yeah.
So that's a virtual image?
That should be a virtual image because the light ray doesn't really intersect this point. One of the light ray do pass through this point, but if you put a screen over here, you will see a whole big spot of light, and you will get something that is really blurry. Any other question? Because a hard one is coming. Suppose I have a lens. I have a fire. I can form an image. A real image is a convex lens, and I can use a screen to show the image. Now, because I can, let me cover the top part of the lens. Then what should I see on the screen? How will that change the image? Is it supposed to miss the top part, bottom part, or upside down, left, right? How should you change the image? Hmm?
Is it convex or concave?
It's convex. You see, this is a upside down image. We just saw that a concave lens will form a convex lens will form a upside down image. So that is a lot of anime. Okay, yeah, back to this question. So it's a convex lens. Yes, convex lens forming an image as it should. And now what you see, what I'm going to do is to cover half of the lens. So we have half, top, bottom, show, down, part, up, question mark, won't, missing, intensity, good. So as I said, this is not the only two light that forms an image. There are a lot of light going through all part of the lens. For this drawing, I only need the top part of the lens, but there are also light coming to the bottom part. So what we will see, all right, anyway, we have experiment. I can show you what I'm saying is true. Here we have Elmo. Elmo is an image formed by the lens. So let me just cover half of the lens. It becomes darker. Okay, I can even put my whole finger here, but the image is still an image. The way my hand affects the image is just letting fewer light pass through the lens. So you still have the full image. It's just the brightness will become dimmer, because the way a lens forms an image is to focus all the light such that they all appear to come from a single point. All the light, not just those passing from the top, but also the bottom. Okay? Any questions? All right. This is important because when you are actually designing some optical device, you have some engineering problem which your lens might be blocked by another lens and you need to drill a hole on the lens, on the mirror, or whatever. You might wonder if drilling a hole on the mirror affect the imaging. The answer is no. You don't need a whole mirror to form an image. You just need part of it. Okay? Now, another thing about lensing I want to mention is your eyeball. You are born with hopefully two lenses built in, and the way your eyeball works is that there's muscle that squeezes your lens and adjusts the focal length of the lens, not the refractive index. Refractive index is a property of material. The material of your lens is not changing, but because you squeeze the lens, you change the shape, the curvature, that will change the focal length. Now, if you are trying to look at something, what your eyeball should do is to make sure the image is formed right on your retina. There are a lot of cells on your retina, and if the image got formed on the retina into a nice and clear image, you can see stuff. But we just saw that the location of object will change the location of image. So if now the object is closer and you still want the image to be formed at the same location on your retina, you have to adjust the focal length of the lens such that when object is at different distance, the image is still located at the same location. So this is how your eyeball should work. When you are looking at something really close, your muscle need to exert force to squeeze your lens such that you can have a image at the same location. Now let's try to guess if you are squeezing your lens, making it a little bit fatter, and focus the closer object onto your retina, is it making the focal length longer or shorter? Is it increasing or decreasing the focal length? Huh? What? Is it a short question? Okay. Never mind. We have increase, decrease, focal, blah, blah, B, A, B, B. Okay, let's make sure I change it. So it should be decrease because if you have let's say you don't have the lens, then it basically corresponds to infinite focal point. So let's look at this point is 36, so let's say 30, 28. So you see what the lens do is to focus the light at one point. So if you want fewer effect such that the lens seems to be not there, if we want to decrease the power of lens, then what we're doing is increasing the focal length. If the focal length becomes further to infinity, then effectively it's like the lens is not focusing light. So it's a weaker lens or less effective lens if the focal length becomes infinity. Or if you want to have a more powerful lens, you want the focal length to be shorter. That can converge the object or converge the light at a shorter distance. And that's what you need when you are looking at something pretty close. When the object becomes closer, the image will move backward. And to make the image come back, you want to increase the power of your lens. So that's decreasing the focal length. Increasing power, decreasing focal length. Decreasing focal length, increasing power. There's a lot of upside down. Increasing refractive index, decreasing speed of wave. Okay. Any question? So what will happen? So we see if you look at something really close, your eyeball will have to squeeze your lens to decrease its focal length. So if you keep staring at something real close, your phone, you stare at it for like 8 hours a day, you might think that's the reason that causes nearsighted. But the biologists tell us that this is not the case. The most recent study about nearsighted is that when you are exposed to sunlight, your eyeball will stop growing. As a kid, your eyeballs start shorter, skinnier, and it will keep growing and becomes longer and longer like this. So when the eyeball is too long, your lens cannot convert the light on the retina. It's just too far away. So this is what we call nearsighted. And the recent research is that the reason that causes nearsighted is because the kids nowadays don't get exposed to enough sunlight. Somehow, for some weird reason, when there's strong enough light, like the sunlight, your brain will produce whatever that stops your eyeball from growing longer and longer. So that's the explanation of why a lot of people wear glasses. They watch iPad at home, they don't go out and play, so they have long eyeball and they have nearsighted. This is important because most of your kids, if you have any, is likely to be iPad kids. So if you want to save money from buying glasses for them, it's fine to have iPads. Just tell them to watch their iPad outdoor. As long as there's enough sunlight, then they'll be fine. All right. So the hardest thing, multiple lens. If you have one lens, you can put more, and the people you fail increase with the amount of lens you put in your final. If the second lens is behind the image, then it's easy. It's the same as treating this image as an object, and you just draw the same diagram like this image is an object. You just do the light ray diagram twice. In this case, the image is a point light source, and one of the light will be parallel after it forms an image. And for a concave lens, you just draw this dotted line that passes through the focal point, and the light ray will be bent toward that direction. On the other hand, if you pass through the center of the lens, it keeps going straight. And you found that after two lenses, the combined effect is that the image will be formed here. Okay? So this is the object. The convex lens forms an image over here, and then the concave lens did a second imaging to turn the object here into an image over here. So this is the easy case. When you have multiple lenses, you just do the lensing twice. Any question? But now comes the hard part. Light is light. It's massless. It doesn't stop you from putting a lens over here. You can form an image behind the lens. So now you have to figure out how to draw this diagram when the object is an image behind the lens. So in your homework, sometimes I will tell you the object is an image behind the lens. That's what I mean. It might be formed by some other lens, some optical device. The thing is that this scenario will happen, so you need to know how to deal with it. So in this case, because of this concave lens, this light ray no longer follows this direction because the lens will change its direction. For the center one, it passes through the center. By coincidence, I choose this light ray, so I don't have to draw more animation. But you see, the image should be formed somewhere else. To figure that out, we want to draw some light ray that pass through some point that we know, that we are familiar with. For example, the focal point. So we want some light ray that pass through the focal point. And if the concave lens isn't there, we'll form this image. This ray do exist. As I said, even though we only draw these two rays, but there's other rays, and one of them that goes a little bit outward will be bended downwards like this and form an image over here. A point to a point, that's how imaging works. And now we want to focus on these two light because I know if the light passes through the center, it passes through the center. If it passes through a focal point, then it becomes horizontal. Okay? So this is how we figure out the light ray when you have a new lens, when you have a second lens between, or when you have a second lens in front of the image formed by the first lens. You just try to choose some light ray that you know how to draw. Okay? And the light ray will form an image if the lens isn't there. You draw those light rays that will form the image when the lens isn't there, and then make sure those light rays is something that you are familiar with, so you can know their new direction after you put the lens over there. Yeah?
So the bottommost light ray, the one that's horizontal, we just go further down?
Yeah?
No, the one at the bottom.
Yeah?
The next point?
Yeah?
Would it just go like more down? Or like
Yes.
upward even more?
Yeah, so if you draw this one, it'll be more downward, but you don't exactly know how much downward. That's why I don't use that one. Yeah?
If like the top light ray, the bottom light ray don't actually go to that bottom point, then why do you see the image at that bottom point?
Oh, I haven't finished yet. You will not see the image here because the light ray doesn't come from here. What you see at the end of these two lenses is a light ray in this direction and a light ray in this direction. They don't intersect here, so you do the trick, which you just try to extend the line backward. And here's your image. Okay? Tricky, right? Make sure you know how to do it. Here's the first lens. Here's the second lens. the first lens form an image here, which is no longer there after you put a second lens. You just draw the light rays to figure out the location, yeah?
Yeah, it seems like it only works when the concave lens is at the focal point of the convex lens.
So that's you have to practice. Here, if I don't put the concave lens at the point over here, I just have to draw a forced light ray to find a new image, but it can be done. You'll see an example later. Any question? Yeah?
Are there two images?
Yeah.
Are there two images?
No, there's only one. So if there's only this lens, no. So if there's only this lens, then the image will be here. But after you add a second lens, the light ray will be bent again, and then at the end of the day, the image will be here. Yeah, any question?
How do you trace back the bottom of the ray?
Bottom one?
Yeah.
So the bottom ray doesn't really go this direction. The bottom ray will be bending more downward, and then if you trace back, it should also pass through the point that the image is located. So all the light ray at the end will look like it comes from this point. But as I said, the bottom ray is going to bend at a direction that you don't really know where to draw. So we don't choose that one. Any other question? So what we see is that in general, you not only need to know how to draw the image when the object is in front of the lens, you also need to know how to draw it if the object is a virtual image or is a image behind the lens or mirror. So here I have a case which maybe there's some convex lens, concave mirror, whatever. Anyway, the object is behind the mirror. You need to know how to draw it. It's usually a good idea to choose a horizontal line that will pass through or that will form this image behind the mirror. You draw this parallel line that will pass through this point, but now because of the mirror, it doesn't pass through this point anymore. No matter what kind of mirror or what kind of device it is, you always know how the parallel line will be deflected. It either go toward the focal point or away from a direction that will pass through the focal point if you extend the dotted line. But anyway, in this case, I know this parallel line will be reflected into this direction. And I can draw another line that will pass through this point. It is important that the line I draw will pass through this point without the mirror, because those lines have to form this image behind the mirror in the first place. So after I figure out two lines that pass through this point, I look at how they will be deflected by the mirror. And for this case, if the light ray passes through the focal point, it will be reflected parallelly by the concave mirror. So your eyeball will see a light ray coming from this direction, you extend it back, and you see an image over here. Okay? Any question? Alright, so your homework is basically to draw more of this. And that's the end. See you on Thursday.